I got the BlackPenRedPen shirt.
Oh, come on.
This video was edited by Sedanimugamez. Look at that epic profile picture. Check him out.
In this video, I'll be introducing complex magnitude, complex argument, and complex loci. First, I'll go ahead and introduce the complex magnitude. Now, what the complex magnitude intuitively is it's going to be the distance between some complex number, let's say z, and the origin. So we usually write the complex magnitude as the magnitude of z, or like an absolute value. Now let's suppose z is, say, a plus bi. So z is a plus bi. Then that means that its real component is a, its imaginary component is b. So the distance a from the origin on the real axis and a distance b from the origin on the imaginary axis. Now you may notice that right here is a right triangle. Now this right triangle has two legs, and I tell you, and I say that we know the two legs. Right there is obviously a distance of a. So the first leg has a distance of a, or a length of a. Then this length right here is obviously b. Alright, now this is clearly a rectangle, so what I can do is this length is the same as this length. So I can move that length across by the fact it's a rectangle. So right there is also b. So this is an a by b right triangle. Alright, well, let's call the hypotenuse c, and this is what we want to find out. Well, you may have seen a triangle labeled ABC somewhere else, and that somewhere else is the Pythagorean Theorem. It's a squared plus b squared equals c squared. C is what we want to solve for, so let's just take the square root of both sides. So I get square root of c squared. The square root of c squared is just c. And then we have the square root of a squared plus b squared on the other side. Alright. This is the complex magnitude. So this is the magnitude of z. Or alternatively, the magnitude of a plus bi. Alright, now the argument is in a similar vein to this, in that you do draw a line between your complex number z and the origin. Just the thing you take is its angle around the unit circle. So that angle right there, theta, is called the argument of z. Alright. Now how do I figure out how to get the argument? Well, let's go ahead and say this is a plus bi. Then what I could do is again draw the components, so that this is a length of b, this is a length of a. Then I can take tangent inverse. So let's go ahead and draw a right triangle like this. Right here's theta, right here's b, right here's a. Let's do the tangent of theta. So the tangent of theta is b over a, which means that theta is tangent inverse of b over a. And so if this right here is a complex number, and the triangle does in fact look like this on the complex plane, then we have tangent inverse of b over a. It's just right here, it's not so simple, because the right triangle angle is actually right here. And this right here is pi minus theta. And so in order to actually get the theta, we have to do pi minus the result we get from here. So this is for theta between pi over 2 and negative pi over 2 and pi over 2. And if theta is outside of that region, meaning it's in one of these two quadrants, then we have to take theta equals pi minus tangent inverse of b over a. And that's just so we get the correct answer. And so this allows us to account for the angle being between 0 and 2 pi instead of just negative pi over 2 and pi over 2. All right. So the argument is the angle, the magnitude is the distance. Now let's talk about complex loci. So now there's two ways to write complex loci. You could say all z such that, and then write out whatever your thing is. And st just abbreviates such that. Or you could write it in set builder notation, which is for all z an element, or we could write it in set builder notation, which involves a curly bracket, and we say that for all z an element of the complex numbers, so this fancy c just means this z epsilon fancy c just means z is some complex number. This is the set of complex numbers. This means an element of. So z is an element of the set of the complex numbers, meaning z is a complex number, such that, and whatever's in there. You usually write a vertical line or a colon. So all z such that, or z an element of the complex numbers such that, in set builder notation. And this just represents a certain set of the complex numbers that obeys a certain condition. So let's do an example. Let's say we have all z such that the magnitude of z is equal to 1. Now what would this look like? So we have the origin, and the distance between z and the origin is 1 for every single point in this loci, which is obviously going to be a circle. It's the set of all points an equal distance away from the origin. So that's a circle centered around the origin. So this loci represents a circle. And I could have also written this as z, an element of c, such that the magnitude of z is equal to 1. That is it in set builder notation. Alright, now let's do something similar, but for argument of z. Let's say all z such that the argument of z is equal to pi over 4. What would this look like? Well, let's go ahead and draw out our complex plane. Let's do a point that is an angle pi over 4 when you draw out that line. So this right here is an angle of pi over 4. Well, another point is, say, this. Another point is out there, and you just get a line. So you get a line that is an angle of pi over 4 from the origin. And this does not include the origin, nor does it include anything continuing this line. So really, it is just a ray. Now the reason why it doesn't go backwards is because of this reason. We define the argument to be different for this quadrant. So this quadrant will have a different angle, namely this angle. So this line right here will have a different angle from this one. So it'll actually have an angle of 5 pi over 4 instead of pi over 4. Meaning that we have to get rid of this portion of the line. And then the origin doesn't have an argument, because you do 0 divided by 0, and that's not alright. Alright. I could have written this in set builder notation, the set of z, an element of the complex numbers, such that the argument of z is equal to pi over 4. Okay, let's do some more advanced examples of complex loci. Let's do the loci of z, an element of c, such that the magnitude of z minus some constant z naught is equal to r. Alright, so z0 is just some random complex number, and r is just some random positive real number. So r here is like, so this is very similar to this loci. The magnitude of z is equal to 1, except it's more general. We replaced z with z minus z0, and we replaced 1 with r. So because this one was a circle, you'd imagine that this one would also be a circle. So let's sort of analyze that. Z minus z0, if you remember, is like a translation to z0. So we translate whatever our function was, and instead of centering it around the origin, we center it around z0. That's what we could do on the real numbers. If we do f of x minus some x naught, you translate it to x naught. So it's the same thing here. And then this r value right here is like the radius, because instead of fixing, alright, so let's start off in our complex numbers, and let's center it around z0. And then this r is the radius of the circle, because instead of, is the radius of the circle, because it's all points a fixed distance of r from z0. And so we have the circle of radius r around z0 given by this loci. And then a similar thing with the argument. So if I have z an element of c, then I have it that the argument of z minus z naught is equal to some theta, and theta is fixed. Well, then this will look like a ray centered at some point z naught, and then we have some angle theta, and we draw out a ray like that. And of course, this is not including z0, because that does not have an angle from z0. Because what is the angle from z0 to itself? You can't really say. There's not enough information, so we exclude it. Alright, now that we have these two generalizations, let's go ahead and prove a very important fact about the magnitude that I will use. Now, the magnitude can be used to define the distance between any two complex numbers, say z and w. What it simply is the magnitude of z minus w. And if we go ahead and graph this, right here is z, right here is w. If I do z minus w, I get this line connecting them. This is just vector subtraction. If you remember vector subtraction, the subtraction of two vectors is just the line between them. And so the magnitude of that is the length of this line connecting them, and so it's the distance between the 2 points. Alright, the fact I was going to prove about the magnitude is that the magnitude of z times w is the magnitude of z times the magnitude of w for any two complex numbers z and w. Alright, let's go ahead and prove it from the definition. So we have the magnitude of a plus bi times c plus di. So a plus bi is z here, and c plus di is w here. Alright, this is going to be equal to just simple complex number multiplication. The two real components are going to be ac, and bi times di. The two i's become a -1, so it becomes ac minus bd. And then plus, it's going to be a times di, bi times c. So those are both imaginary components. So ad plus bc pi, magnitude. Alright, let's use the definition of the magnitude. We have the square root of ac minus bd squared. This is the real component, plus ad plus bc quantity squared, the imaginary component. Alright, this is then equal to the square root of, let's just do foiling. I get a squared c squared minus 2ac bd plus b squared d squared. That is just simple foiling on this first example. And then I add that with this component, which gives us a squared d squared plus 2adbc plus b squared c squared. So those are the two different components multiplied out. Then, right here you can see that there's an a, there's a b, there's a c, there's a d. So this is really just 2a, b, c, d. And right here you can see there's an a, there's a b, there's a c, there's a d. This is really plus 2a, b, c, d. Minus 2a, b, c, d plus 2a, b, c, d. So this is equal to, canceling those two terms out, a squared c squared plus b squared d squared plus a squared d squared plus b squared c squared. Alright, now this is going to be equal to, let's do a squared c squared. Let's move this a squared d squared right there. And then I'm going to move this b squared d squared right there. And I'm going to leave the b squared c squared right at the end. Now what I'm going to do, both of these terms have an a in them, both of these terms have a squared in them, and both of these terms have b squared in them. And so I can group them. So right here I have a squared quantity c squared plus d squared. That's just from grouping. And then plus b squared times d squared plus c squared. So both of those were just grouped and or factored so that it looks like this. Now notice c squared plus d squared is the same as d squared plus c squared. So let's go ahead and flip the order on the addition there. So it reads c squared plus d squared. So now you can see it. We can now group out c squared plus d squared. So we get the square root of a squared plus b squared. That's the first term, there's the second term. And then grouped out with c squared plus d squared. Then by the fact that these are all positive real numbers, we can separate it out into two square roots. One of a squared plus b squared, the other of c squared plus d squared. And that's a multiplication there. And you can see by the definition of the magnitude, this is the magnitude of a plus bi times the magnitude of c plus di. Bruh. Look at that. Magnitude of a plus bi times c plus di equals magnitude of a plus bi times the magnitude of c plus di. The magnitude of the product is the product of the magnitudes. Very cool. Oh my god, that took too long. Anyway, now let's talk about some more advanced examples of loci. So let's say we have z minus 1 divided by z minus 2. Alright. We do the magnitude of it, and we set it equal to 1. Now, how on earth am I supposed to figure out what this looks like? Well, using this fact, and because division is just glorified multiplication, I can move this to become the magnitude of z minus 1 on the top, and the magnitude of z minus 2 on the bottom, and that's equal to 1. So I have it that the magnitude of z minus 1 is equal to the magnitude of z minus 2. Alright, now let's go ahead and write z as x plus iy, just so we can tell what's going on here. So we have the magnitude of x plus iy minus 1 equals the magnitude of x plus iy minus 2. So this gives us magnitude of quantity x minus 1 plus iy equals the magnitude of quantity x minus 2, just factoring in the real parts of these subtractions, plus iy. Now using the definition of magnitudes, we get the square root of x minus 1 squared plus y squared equals the square root of quantity x minus 2 squared, the real component, plus y squared, the imaginary component. Alright, Now we square both sides to get rid of that nasty square root, and we get x minus 1 quantity squared plus y squared equals quantity x minus 2 squared plus y squared. Now x minus 1 squared, let's go ahead and FOIL that out. We get x squared minus 2x plus 1 plus y squared is equal to, FOIL that out, x squared minus 4x plus 4 plus y squared. Now you can see there's a y squared on both sides. Can cancel those out. There's an x squared on both sides. We can cancel those out. Now the only thing that's left is minus 2x plus 1 is equal to minus 4x plus 4. And that's just a simple equation. So that's plus 2x minus 1 plus 2x minus 1, which, doing this out, 0 on the left-hand side and negative 2x plus 3 on the right-hand side, which, pretty obviously, it's a one-step equation, gives us 3 over 2. Which is weird, because we started off with this magnitude expression, and somehow we ended up with just a constant real part. So if I were to graph this, it'd look like that. Just a vertical line. Starting off with this huge magnitude expression, it's simply a vertical line, which I think is really cool. But it is also very anticlimactic. How all that work just got us to a line. So my challenge to you is to replace that 1 in the original problem with a 2. See what comes of it. See what the solution is and how to graph it. So send me your answers in the comments. I always read my comments, so I'll probably see your answer. And if you have a particularly good answer for this, then I might put you in a video. Anyway, that's it.